This is our new paper from BSc second, real analysis first, that is remaining from our syllabus, offline syllabus. So, in that paper, we first learn two units, functions and countable sets. Okay. So, theory of sets, we know we have taken one lecture or two. See, revision of sets, finite set and infinite set. So if we start counting the number of elements in a given set, and if this process of counting comes to an end at some stage, then the set is said to be a finite set. And if counting is not ended, then we say it is the infinite set. If the process of counting does not stop at any stage, then it is called an infinite stage. So there are some methods for specifying sets. The roster method, we know all these things. Set builder method means, see, written in this way. This is roster method. This is set builder method. So these are the preliminary things. So we know the sets, that is the set of natural numbers, set of all integers, Z or I. Q means set of rationals of the type P by Q, or the set of all reals, C the set of all complex number. We are familiar with this, no problem. So singleton set means a set containing exactly one element is called a singleton set. Okay. So these two are examples, that is they are the singleton sets. I will send this PDF copy to the WhatsApp group, no problem, but understand some things. So null set and or empty set. So null set means the set having no any element, we call that is a null set. So example is x belongs to R such that x square is minus 9. So for this equation x square is equal to minus 9, there is no any x, that is the solution of this equation, a real number. So it is given, it is x belongs to R. That's why this set is a empty set. Similarly, this is also empty set. Note that sets 0 and 5 are not empty sets. Subset of a set, these are the preliminary things. What is meant by subset? We know these things, so we are not wasting the time in this. So, proper subset, that is, if A is 2, 3, 4 and B is 1, 2, 3, 4, then A is proper subset of B. Proper subset. Okay. Power set, we know set of all subsets of A is called power set of that set A, denoted by this P of A. So if example is given, if A contains two elements A and B, then power set of A contains that is A, B and empty set also. So empty set is subset of all sets, we know that. Equality of two sets are said to be equal if they have same elements. That is A is 3, 4 and B x belongs to R, so that x square minus 7x plus 12 is 0. Solution of this equation, we know, we get the values 3 and 4. So these two are A and B are equal sets. So universal set, we are this one familiar with this. Venn diagram means, see in this way, these are the X, the universal set, A, B, C, these are the subsets of this one. So we call this is the Venn diagram. We have studied this in the 11th and 12th standard, no problem. Operations on sets, that is arithmetic operations, addition, multiplication, subtraction. So union of sets. So what is meant by union? Intersection, we are familiar with these. Again, we are not wasting time in this one. So properties means A union B means B union A. This is commutative law. A union B union C means A union B union C. We can write the brackets in the front. A is subset of A union B, B is subset of A union B. If A is subset of B, then A union B is equal to B. In particular, A union X is X, because X is the universal set. A union phi is A. These are the properties. So, intersection of sets means we know this is the common elements containing in these two sets. So, what is meant by intersection? We also know these things. Disjoint sets means intersection of these two sets is an empty set. Then we call it is the disjoint set. That is, two sets A and B are said to be disjoint. If A intersection B, E is equal to 5. That is, A is example is A is 5, 6, 7, 8, B 1, 2, 3, 4. Then A and B have no common elements, and as such A intersection B is an empty set. Then we say this A and B are the disjoint sets. So there are properties of intersection sets. So A intersection B means B intersection A, all these things completely associative law. A intersection A means A intersection phi is phi. A intersection phi is phi. A intersection X is A. A is subset of B, then A intersection B is A. In this way, A intersection B is a subset of A, then also A intersection B is subset of B. Complement of a set, if A and B are two sets, then the complement of A relative to B is the set written in this way, B by A. That is, X belongs to B, but X does not belong to A. This is the complement of any set. Irrespective of the complement, irrespective or relative to the universal set, we know all these things. So this is complement of B relative to A, and this is complement of A relative to B. So Venn diagram means complement of A and X is the universal set. So see, A सोडून सगळे असतील ते त्या A complement मध्ये असतील. So A and B are in this way, then B minus A and A minus B. So here is a means we get complement of B in A and this is complement of A in B. So complement of a set related to universal set. So we know these things. So properties of complement: A complement is A, X complement is phi, phi complement is X. So all these things, symmetric difference of two sets. Symmetric difference means if A and B are two sets, then symmetric difference of sets A and B is the set A minus B union B minus A, and it is denoted by this symbol A triangle B. We call this is the symmetric difference of sets A and B. So A and B are the sets in this way. A contains 1, 2, 3, 4, 5, 6, 7, 8, up to 7, and B is 1, 3, 5, 7, 8, 9. Then A minus B means it is 2, 4, 6 only. A minus B means 2, 4, 6 only, and B minus A means 8 minus 8, 9 only. So relative, that is symmetric difference of these two sets is the union of this A minus B and B minus A, and this is the 2, 4, 6, 8, 9. So these are the preliminary things. Idempotent law, we know that for any set A we have A union A is A and A intersection A is A. Identity laws for any set A we have A union phi is A and A intersection U is A. Intersection is A there. Find U are the identity elements of union and intersection respectively. Identity, and that is phi, and U means universal set. These are the identity elements for union and intersection. Okay. Commutative laws for any two sets A and B we have A union B is B union A intersection B is B intersection A, no problem. So associative law, distributive law. So we know these De Morgan's laws are important one. That is A and B are any two sets, then A union B its complement is A complement intersection B complement, and A intersection B its complement is A complement union B complement. Above laws can be easily proved. Here are we provide proofs of De Morgan's law. It is not need to learn the proofs of this. Only remember what are the De Morgan's law in case of union and intersection. So proofs are not important. So only see the statements of this theorem. If A, B, C are sets, then A minus B and C can be written as A minus B. Intersection A minus C. May be asked in case of that is multiple choice questions. A minus B union C is A minus B intersection A minus C, and here is union. So these are the theorem. So we are not going to learn the proof of this. So list the elements in the following set. The set of all integers greater than 7 and less than 15. Set of all integers greater than 7 and less than 15. So solution, that is A x belongs to Z, x is greater than equal to 7, less than equal to 15. Means actually 8, 9, 10, 11, that up to 14 only. So set of all integers 1 to 14 which are multiples of 6. That is set of all integers. That means between 1 to 40 multiple of 6 are 6. So required set is here in this way. Set of all letters in the word banana. So set of all letters in the word banana means only BAN. not B-A-N-A-N-A, repetition, that is, objects must be distinct there in the set. Set of all integers between 50 to 60 written in this way. Set of all integers from 1 to 50 having 3 as digit in one's place. So here, these are the simple cases, no problem. So, these are the preliminary things where omit this. So, all these are the simple. Cartesian product of the sets. Let A and B be two non-empty sets. Then the set of all ordered pairs x, y, where x from A and y from B is called Cartesian product of the sets A and B. It is denoted by A cross B. Thus, A cross B is the set of ordered pairs. It is important. Set of ordered pairs. So x must from A and y must from B. So see the example is given. So what is meant by Cartesian product of the two sets? So if A has 2 elements and B has 3 elements, then Cartesian product of these two sets contains 6 elements. 3 into 2, that is 6. Here is something is wrong there. That is, here is 2 into 3, not 3 into 3 there. You can understand it, no problem. So definition, if A and B are two non-empty sets, then a relation R from set A to set B is a subset of Cartesian product A cross B. Relation from A to B is a subset of this A cross B. So R is a relation from A to B if and only if R is subset of A cross B. So what is meant by relation? We have studied in the previous paper. So see domain and range of the relation. So what is meant by domain and range? We know that. So we have studied this one. So this is just a revision. So illustration means example is here. That A set contains these 4, 8, 12, 16, 20. These are the 5 elements, and B contains 5 elements, 1, 2, 3, 4, 5. And the R is a relation from set A to set B. And the relation is here, that is ordered pairs 4, 1, 8, 5, 12, 16, 3. Then R is a relation from A to B. So domain of R is 4, 8, 12, 16. And range of R is 1, 5, 2, 3. It is here. What is meant by domain and range? So A is ABC and R is a relation from A to A. We call this is A to A relation. That is A cross A. R is a relation. R is subset of A cross A. R is a relation on the set A. We say that. So it is not need to say that is our relation from A to A. Only we say R is a relation on set A. So this is the relation A, B, B, A, B, C in this way. So inverse relation means we can reverse the ordered pairs only. This is the inverse relation. So here is one example. See, we learn. So A is 1, 2, 3, B is 4, 5, 6. Which of the following are relations from A to B? Give reason in support of your answer. 1, 6, 3, 4, 5, 2. Relation from A to B. So 1, 6, 3, 4 and 5, 2. This ordered pair does not belong to that relation. So 1 is not a relation. So that is 5, 2 does not belong to A cross B. 5, 2 does not belong to A cross B because relation is a subset of the Cartesian product, because R is relation from A to B. So 1, 5, 2, 6, 3, 4, 3, 6. So the problem second is a relation. R2 is a subset of A cross B. R2 is a relation from A to B. 4, 2, 4, 3, 5, 1. This is not relation. This is 4, 2, 4, 3, 4, 2, 4, 3, 5, 1. This is not relation. So this is not subset of A cross B. It is subset of B cross A. So it may be relation. That is, if relation is B to A. A cross B is a relation, no problem. Because A cross B is a subset of A cross B. Okay. So if A is the set of first 5 natural numbers and R be the relation on set A defined as x, y belongs to R, which implies x is less than equal to y. Express R and its inverse as the set of ordered pairs. So A is the set, it is given 1, 2, 3, 4, 5. R is the relation on A given by x, y belongs to R such that x is less than equal to y. 1 is less than equal to 1, 2 is less than equal to 2, 3 is less than equal to 3. So all these are the, that is x must be less than or equal to y. That is 1 1 there, 1 2 there, 1 3 1 4 1 5 there, 2 2 there, 2 3 2 4 2 5 there, 3 3 3 4 3 5 there, 4 4 4 5 5 5 there. So this is the R relation from set on the set E. Its inverse relation means we just reverse these ordered pairs. We get the inverse relation of that. So determine the domain and range of relation R defined by R is equal to x plus 1, x plus 5, the ordered pairs of this type. X belongs to 0, 1, 2, 3, 4, 5. Okay. Here it is R is x plus 1, x plus 5, such that x belongs to this set 0, 1, 2, 3, 4, 5. Means x is from this set. So take on x 0, then 1, then 2. So we get all these ordered pairs. So just to determine the domain and range. So from this we can write the domain and range. We can write if x is 0, then we get 1, 5. If x is 1, we get then 2, 6. If x is 3, then we get 4, 6. In this way. For it in this way. So we know domain means what and range means what. So write the following relation as set of ordered pairs. A relation R on set 0, 1, 2, 3 dot 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 defined by 2x plus 3y is 12. A relation R from set A to the set B defined by xy belongs to R equal to x divides y. So R is a relation on set these 0 to 10 numbers given defined by 2x plus 3y must be equal to 12. So A is in this way R relation on set A, R is subset of A cross A, no problem. A cross A contains ordered pairs xy, so that xy belongs to A. So 2x plus 3y is 12 means y is equal to 12 minus 3, 12 minus 2x upon 3. So now put x 0, 1, 2, 3, we get the values of y, and here are the values of x. Okay. So how many ordered pairs? So we observe that R is 0, 4, 3, 2, 6, 0. These are the only ordered pairs, because if x is 0, then we get it is 4, and that is in set A. If x is 1, we get 10 by 3, and it does not belong to set A. So 1 and this 10 by 3 ordered pair does not belong to this relation. So this is the new thing here. So there are so many examples for relation. So in the first paper we have studied the relation. So many that is reflexive, symmetric, transitive, whatever may be. So we are familiar with the relations. So now we have seen the functions also. So relation from set A to set can be a function under some conditions. So what is meant by function? We have studied notes इथं आहेत तुम्हाला दिलेले असतील त्या थोड्या बघितलं तर चालतील. So domain, codomain, range of a function. We have studied this one. Direct and inverse image of a subset. So here we are not wasting time in this. So only remember this statement of this theorem. If f is a function from set A to B and f x is subset of B and y is subset of B, then f inverse of x in n y is f inverse x in n f inverse y. Not try to understand that is do not waste time in this to understand the proof of this one. So in case of intersection, the theorem is here. So again there is a proof. So if next theorem is f is a function from A to B, and if x is subset of A, y is subset of A, then f of x in n y is f of x in n f of y. So this is again in case of intersection there. This is the illustration. That is their example. So injective, surjective, bijective, and inverse functions means this is 1 1 onto and 1 1 onto. We say that. So that is injective, surjective, and bijective function. A to B be a function from set A to set B. The function f is said to be injective if for x1, x2 belongs to A. X1, this is understand this. What is this? x1 not equal to x2 implies f of x1 not equal to f of x2. Or equivalently, we can say that is f of x1 equals to f of x2 must implies x1 is equal to x2. Then we say that function is 1 function. So this is a 1 function. A to B is 1 but G is not 1. See, figure, understand it carefully, the definition of 1 function. This is x1 is related with y1 and x2 related with y2. So these two elements related to the same element. So this is a many one. This is not 1 but this is a 1 function. Okay. So surjective function, that is means onto function, means codomain set and range must be equal. That is, range of f must be equal to codomain set. Then we say the function is onto function. Bijective means if function is 1 and onto, then we say it is a bijective. That is, if it is injective as well as surjective, then it is called the bijective function. If f is 1 and onto, then it is a bijection function. Also, it is called bijection. So, so this is an example of that is a bijective function. This is 1 and onto. Okay, 1 and onto. That is the range of this function is equal to codomain set, and is also a 1 function. So inverse function. Here is an inverse function. If f is function a to b is 1 and onto function, then we define y is equal to f of x belongs to them. Then we define g b to a as the inverse function of f. That is, when the inverse of function exists, that function must be the injective and surjective. That is, that must be 1 and onto. Then only inverse of that function is defined. Otherwise, not. Okay. So proposition means say now if f a to b is injective means 1 and E is subset of A, then f inverse of f of E is equal to E. Remember the proposition, not the proof of this one. So if f a to b is surjective means onto, then and h is subset of B, then f of f inverse h means h actually. Composite functions means what? See, if f is a function a to b, g is a function b to c, then only composite function is defined, that is from a to c, written as g of f of x. Okay, order is important there. That is, here is definition: f a to b and g b to c be two functions. Then the composite of functions f and g is the function written g composite f from A to C, that is G composite F from A to C is given by G composite F of X is G of F of X. Okay, this is from A to C. For composite map, that is function, map means function, G composite F, range of F must be a subset of domain of G. These are the properties or remarks, the problem. So here are some examples means how to find the composite functions f and g given, that is fx and gx given. We have to find f composite g, g composite f, f composite f, and g composite g. So f first is f composite g of f f composite g of x is f of g of x. F of g of x is given x square plus 1, but fx is x plus 5. Now this is defined as this is x plus 5 means we get f of g of x. In this way, g composite f of x, f composite f of x, and g composite g of x. So there are some examples there. This is the restriction and extension of a function. Suppose f and g are two functions with respect to x and y, and if x is subset of y and if fx is equal to gx, then we say that this is for x belongs to domain of that domain's x. Then we say that g is extension of f. Do you get this point or not? See, I will clear this point. So let here it is in this way. See now. This is y and x axis. So, and we know that this is the graph and this is straight line, and we know this is the equation of this is y is equal to x, and here x belongs to the closed interval, that is half closed interval 0 infinity, means this is the domain of this function y is equal to x, or fx is x. One more graph I want to plot. This is x and y axis, and origin is here, we know that. So this is the graph of the function y is equal to modulus of x, and x belongs to R, that is R is the domain of this function. Clearly this is extension of this one. Okay, suppose this is instead of y we say this is g of x, and this is f of x. Fx is x and this is g of x is mod x. Clearly fx is equal to gx for the domain of f only. Okay, clearly modulus of x चा ग्राफ असा आहे आपल्याला माहिती आहे, आणि हा याचा काय एक्सटेन्शन आहे. मग काय एक्सटेन्शन कशाला म्हटलं एक्सटेन्शन, x मस्ट बी सबसेट ऑफ y, मीन्स fx चा डोमेन जो आहे तो gx च्या डोमेनचा सबसेट पाहिजे, आणि fx बरोबर gx पाहिजे कुठल्यासाठी, तर x बिलॉंग्स टू डोमेन ऑफ f of x. सो दिस इज द एक्सटेन्शन ऑफ द फंक्शन r. आता हे gx इज एक्सटेन्शन ऑफ fx म्हणतोय आपण इथं, दुसरं नाव त्याला fx इज रिस्ट्रिक्शन ऑन gx असं आहे. हे दोन वेगळं नाही, रिस्ट्रिक्शन आणि एक्सटेन्शन वेगळं नाही, फक्त ते आपण कसं घेतो त्याच्यावरती. ओके, सो वी क्लियर इट. ओके, दिस इज रिस्ट्रिक्शन अँड एक्सटेन्शन ऑफ द फंक्शन्स. Mathematical induction, we take this the next lecture. This lecture I will send in on YouTube, and it's a link on the WhatsApp group, no problem. Okay, this is sufficient for this small lecture. We take the 4-5 lectures for this paper. Okay, thank you.